the objectives of chapter 1. Basically, we will learn a new language, the vocabulary of thermodynamics. I am sure many of the terms that I will use, you heard them before, okay? But in thermodynamics, many terms have, I think, well-defined meanings. So it is important to understand what certain concepts mean in thermodynamics for the sake of being precise. So it is important, to have a precision in language. Okay, and we will talk about the units. Now you may say, well, we are tired of units. We have seen it so many times. The reason we do units is that, again, people make a lot of mistakes, even engineers, on the use of units. Even in major projects, people make mistakes, and often the projects are, cancelled because of some unit error, which was done at the early stages of a project. And the basic concepts of thermodynamics we will go through. We will go through some properties that like density, specific weight, whatever, just to make sure that we are on the same wavelength. We will discuss the temperature and pressure, the things that but still, just to make sure that we see eye to eye, we will go through them. And finally, some problem-solving technique in engineering. That is how to solve engineering problems in a systematic manner. Okay, and these are the different sections. So first we'll discuss thermodynamics and energy, which we just did, the importance of dimensions and units. We will discuss systems and control volumes because they are different, and then properties of a system, in particular density and specific gravity, and specific volume, because they are important. We will discuss state and equilibrium, processes and cycles, and then temperature and pressure. Okay, and hopefully we will do it today within the next 2 hours. Now, thermodynamics, of course, the first question that comes to mind is, what is thermodynamics? The very short answer is, thermodynamics is the science of energy. That is anything that deals with energy. Therm is like heat, and dynamics is like motion. So energy in motion, so conversion, transformation, transfer, whatever. Anything energy is and energy does. It is the topic of thermodynamics. And the foundation of thermodynamics is the conservation of energy principle, which we call the first law of thermodynamics. And just to give an example, for example, probably some of you are on a diet trying to lose weight, and some, of course, do the opposite, they want to gain weight. Okay, what is the basic principle involved when you are on a diet? Basically, you look at your energy input. Okay, that is how many calories you are taking, and then how much energy you are spending. That is, do you exercise enough? And your body, of course, uses certain energy because your lungs are working, your heart is beating, your brain is working. So you use a certain amount. But if your muscles are also, working, like you are walking, running, whatever, then you burn a lot of calories. So the conservation of energy says the energy in minus energy out is what? Energy storage. Okay, which means if you take in more energy than you expend, you will gain weight. This is the first law of thermodynamics. Okay, of course, the second law says, well, the efficiency of the body is also important. Some bodies are very efficient and some bodies are not. Somehow we want everything to be very efficient, but we want our bodies to be non-efficient. That is, we want to have a lot of energy input, but not to gain any weight, weight here. Okay. And in this course, we will deal with classical thermodynamics. Okay. So we will not deal with individual atoms and molecules, whatever. Which is statistical thermodynamics. Later on, you may have a course on that one. And the second law, just to give you a sense, again, let's say we have coffee at 70 degrees and the environment is at 20 degrees, okay? We know that heat will be transferred because of this temperature difference from the coffee to the air outside, okay? And now, if we have heat from the environment entering the coffee so that the coffee temperature rises to, let's say, 75 degrees, will it violate the first law of thermodynamics? The answer is no, as long as the heat lost by the air is equal to the heat gained by the coffee, the first law is satisfied. But the second law says heat can only be transferred from high temperature to low temperature. Okay? Otherwise, it will violate the second law. That is, heat never goes uphill, just like water. Heat always flows downhill. Again, just like water there. Okay, this is the second law. And one question in your mind may be, where will I use thermodynamics? Where is it used? The short answer is, there is hardly any place where thermodynamics is not used. That is, thermodynamics is used everywhere. So it is important, to have a good understanding of energy here. And you will appreciate this course later on. For example, the refrigerator, okay? In your house, it is entirely thermodynamics. If you look at, let's say, the ships, okay, the boats moving on the oceans using energy, whether it is wind or gasoline or nuclear power, it is again thermodynamics. Aircraft, airplanes, again a lot of energy conversion involved there, and cars, okay. The fuel being converted to heat and then being converted to mechanical power. A lot of energy conversions. Human body is like a heat engine there. Power plants, okay, wind turbines. I don't know, industrial facilities, even the kitchen. That is, you use thermodynamics really everywhere. For example, if you have a solar collector, solar water heater, or PV on your roof, again, a lot of energy conversion. So you use a lot of thermodynamics here. That you cannot do the calculations, the design, unless you know thermodynamics. I can assure you that thermodynamics is an important course, an important science, and you will benefit a lot from learning this science. Okay, dimensions and units. You have seen this a lot. Okay, so I will not go through a lot of detail here. I just point out certain things. Okay, the units. I will emphasize the units. The dimensions you are already familiar with, and two unit systems: the SI, okay, Systems International, the metric system, or the English system. Almost the whole world is using SI, except some countries, and United States also included. They are mostly using still the English system there. Okay. And the basic dimensions, we have like the length. The unit is a meter, mass, the unit a kilogram, etc. You know those things. And those prefixes in SI, okay, they are also important. Kilo, for example, simply means 1000. Like kilogram is 1000 gram. Mega is million. So megawatt is 1 million watts. Okay, giga is like billion. Okay, tera is whatever. If you know, at least you know some of these words like this, they are used a lot. Okay, I think it is good to know. The other ones you don't have to know unless you are in particle physics or something. Okay. Now some SI units and some English units. First of all, the mass unit in the English system is pound mass. Okay, in SI it is a kilogram, and 1 pound is about half a kilogram. And lengthwise, 1 foot in English system is 1/3 meter, about. Okay, and force is mass times acceleration. Therefore, if you take a 1 kilogram mass, okay, and you accelerate it by 1 meter per square second, the force needed is 1 Newton. So this is how we define Newton. So 1 Newton is the force needed to accelerate 1 kilogram of mass by 1 meter per second square. In the English unit, it is something similar. Therefore, here is a unit conversion for you. 1 Newton is 1 kilogram meter per second square. Now it is important to learn this because when you do unit cancellations, calculations with the quantities, okay, you always have to use units. Otherwise, you can make a lot of mistakes. So keep in mind, 1 Newton is 1 kilogram meter per second square. In English unit, it is 32.174 pound mass foot per second square. Okay, now work, again, from high school, you remember, work is force times distance. And the force unit is Newton, okay? Distance is meter. So the work unit will be naturally Newton meter. And we call Newton meter a joule, okay? So 1 joule is always 1 Newton meter. Just to keep in mind, 1 calorie is 4.1868 joules, okay? And 1 BTU is about 1 kilojoule there. Now to help you visualize, okay? First of all, weight is the force of gravity acting on a subject of mass m, okay? So it is mg, and if you take a mass of like 0.1 kilogram, okay, and the gravitational acceleration is 9.8 meter per second square, okay. So from weight is mg, if you multiply them, it is almost like 1 Newton, right? 0.1 times almost 10. Therefore, it gives us, you know, a new definition for Newton to help you visualize. It is simply the weight of an apple, which is 102 grams. Okay. You can imagine the weight of a apple. So 1 Newton is that force, the force of gravity acting on a kind of a medium-sized apple. Now, if let's say we have a mass of 1 kilogram, Okay, what is the weight of it? Okay, you multiply this by 9.8 meter per second square. Okay, so this is like 1.8 Newton. That is, the weight of 1 kilogram is 1.8 Newton. Okay, and we call this one 1 kilogram force. So the weight of 1 kilogram is 1 kilogram force. It is not an SI unit, but it is used a lot in the industry. Therefore, it is good to know it. 1 kilogram force. Okay, and here in the picture you can see 1 kilogram force is simply the weight of 1 kilogram, which is about 1 kilogram apples, right? The mass doesn't change no matter where you go, but the gravity changes because it depends on the force of gravity. If, let's say, you go to the moon, okay, then you will weigh a fraction of what you weigh right now, about 1/6. Here, if, let's say, you weigh 66 kilogram force, when you go to the room, you will weigh only 11 kilogram force. So a very fast way to lose weight if you want to lose weight. Okay, to make them again more visible, okay, as you see here, 1 kilogram weighs 1 kilogram force, and 1 pound mass weighs 1 pound mass, 1 pound force there. Okay, how about the energy unit, BTU or kilojoule? If you burn a match, the amount of chemical energy, the heat released here, okay, from this one match is about 1 kilojoule. Okay. In an equation, it is important to have dimensional homogeneity. That is, dimensional to be homogeneous, meaning in an equation, every single term must have the same unit. Okay. Otherwise, that equation is not valid. And also keep in mind that you can always multiply terms by 1. Okay, the value doesn't change. Therefore, you can, let's say, multiply any term by 1 Newton divided by 1 kilogram meter per second square to do unit cancellations there. We call these energy conversion ratios, which are equal to 1. And in calculations, you can always use energy conversion ratios. For example, 1 minute over 60 seconds. Okay, it is the same thing, right? 1 watt is 1 joule per second. Okay, so they are the same thing. 1 Newton is 1 kilogram meter per second square, etc. That is, when you do unit cancellation, sometimes using these ratios, unit conversion ratios, may be very helpful there. For example, you are calculating the weight of something, okay? Something which is that many grams, and G is 9.81 meter per second square. But what is the result here? The result is like 4.49 4,490, let's say, gram times meter second square. Okay. We never use such a unit for weight, right? How much do you weigh? You say that many kilogram, what we mean is a kilogram force. Gram, meter, second square. We don't do that. So we need obviously a conversion. Okay. So if you add here like 1 Newton per 1 kilogram meter second square, and then 1 kilogram divided by 1,000 gram, okay, this conversion ratio, then what happens here? This, if you divide this by 1,000, so 1,000 gram and this 1,000 gram will cancel, and you will get 1 kilogram. And then 1 kilogram meter second square will also cancel that meter second square. You end up with Newton. So here you get Newton. That is, all the units cancel out nicely, and you end up with the right unit there. Or what you can do is you can say this is equal to, okay, divide by 1,000, 4.49 kilogram meter second square, but you recognize this kilogram meter second square as Newton. Okay, so you say this is equal to 4.49 Newton. Okay, but make sure that you do this unit manipulation. The worst thing you can do is, okay, weight is equal to mg. What is m? 454. And what is g? 9.81 equal to 4,490. Okay. And what is the weight? It is Newton, and put a Newton there. This is what you often do. That is, you multiply the given numbers and then put down the force unit. And you can see that this will cause a large error, a factor of 1,000 here. So always use unit manipulation. Okay. So that should be enough for emphasis on units. Okay. Now systems and volumes. Now what is a system? It has different meanings in different areas. In thermodynamics, it is anything that you study. It can be a quantity of matter. It can be a region in space. Okay. Anything you choose for analyzing. It is your system. And what is surroundings? It is anything which is outside the system. And what is a boundary? The boundary is that imaginary surface between the system and the surrounding. And the boundary can be fixed or moving. For example, the dashed line here is the boundary. Okay. And the mass inside is a system. We will call it closed system. And this part of the system, see this part? This is moving boundary. Because as the piston goes up, that boundary will move. But this part is fixed boundary. That cannot move. Okay. So this is the system. Anything outside the surroundings. And that dashed line is boundary. Okay. And this is the moving boundary. And that part is, this part is the non-moving boundary. And here we notice that the amount of mass inside is fixed. Okay, it is constant. And if the mass is fixed, and if you choose that mass for analysis, it is called a closed system. So this is a closed system. If you have a closed system, as you see, mass cannot enter or leave the system, but energy can. That is, you may have like a heat transfer here. You may have here, let's say, work leaving the system, work energy, but no mass can enter or leave. This is what we call closed system or control mass. Open system or control volume. It is the space that you choose, the region that you choose for analysis. Okay. For example, let's say you have a water nozzle and you want to analyze the nozzle. Okay, this is the nozzle real boundaries. Okay. if you choose the space, the region within the nozzle like this, okay, as your system, it's a control volume. And as you see, mass enters and also mass leaves. It's a control volume. And this is a real boundary here, but this is imaginary boundary because a mass can penetrate there. And a control volume can involve also a fixed boundary, as you see here, or moving boundary. This is a control volume because mass is entering, crossing the boundary. Okay, so this is what we mean by a system, a closed system or fixed mass, and control volume or an open system. For example, this water heater, is that a closed system or control volume? What do you think? Anybody? Well, what happens to a water heater? Do we have water entering? Cold water entering, and then hot water leaving, right? And what do we analyze it? What goes on in this water heater? So what is a proper choice for system? To choose this region as the control volume, okay? So that mass enters and mass leaves, and we may have, let's say, a heat loss here, and we may have electrical work, okay, entering. There may be like electric heater inside. So this is a control volume there. Okay, any questions so far on system, control volume, boundaries, mass interaction, energy interaction as heat work? Any questions on that, on those concepts? Very clear? Okay. Now properties, okay? You also know properties because they are things like, you know, mass, volume, temperature, pressure, density, whatever. Now in thermodynamics, we classify them properly, okay? We divide properties into two groups. One is intensive properties, the other extensive properties, okay? And intensive properties are the ones that are independent of the extent of the system. That is the mass of the system. Examples, temperature, like T, and then pressure and density, okay? Even if you double the system, they will not change that. They are intensive properties. And extensive properties are the properties that depend on the size of the system. For example, mass are extensive property, and volume is an extensive property. And what is a criteria to distinguish between intensive and extensive properties? You simply, let's say you have a system, you divide the system by half, as you see here, okay, to equal parts. The intensive properties, they remain the same. That is, the temperature doesn't change for each part, but extensive properties go down by half for each part. Let's say the mass originally was m, right now the mass is half m for this part, okay? And the volume is half the volume. And the energy is, again, half the energy, total energy. But density, pressure, temperature, they are the same in both parts, okay? So this is how we distinguish between intensive properties and extensive properties. And also, we assume the properties are homogeneous. Normally, what do we have? Let's say we have really vacuum. That is, we have atoms, let's say, in the air at certain places. And if you take an atom, okay, like oxygen, and then look at the inside, we have the nucleus here, something very small, okay. And then this is vacuum. And when we say temperature, where is the temperature that we are measuring? Okay, if you consider the atoms like this, you cannot get anywhere. So what we do is we assume that matter is homogeneous. Okay, that is, no matter where you measure temperature, pressure, density, whatever, it has a homogeneous value. We do not consider the atomic nature of the substance here, unless you deal with particle physics. Okay, in engineering, we deal with systems that are larger than several atoms or molecules. So we don't deal with those, even in chemistry. Okay, so this is called the continuum assumption there. And I'm sure you remember density, again from physics, even high school. It is mass per unit volume. In thermodynamics, we often use, traditionally, the inverse of it. That is specific volume, because density is like specific mass. Okay, specific volume is volume per unit mass, and it is determined by dividing total volume by the total mass. As you see, it is the inverse of density. So if you know the density, the inverse of it is what? Specific volume. Example, you have a tank, 12 square meters, and the mass is like 3 kilograms. What is the density? Mass divided by volume. Okay, mass divided by volume. It is 0.25 kilogram per square meter. What is the specific volume? It is volume divided by mass, 12 divided by 3, which is 4. Or just take the inverse of density there. Okay. Another property we have is specific gravity. Okay. I think a better name is relative density, really. Now, often we express the density of a substance relative to the density of a well-known substance like water at a certain temperature, like 4 degrees, okay, with a density of 1000 kilogram per cubic meter there. It is called a specific gravity. So the specific gravity of water is 1. Gold is 19. So gold is very heavy, and air is 0.001. It is the reason that 1000 cubic meters of air will weigh about 1 kilogram, whereas 1 liter of water weighs 1 kilogram. Okay. And another property we often use is specific weight, which is density times the gravity. Okay, so it is Newton per cubic meters. We don't use specific gravity and specific weight very often, but sometimes they are used, so you should know what they are. Now, as a little example on unit conversions again, the question here says that shows that 1 kilogram of mass 9.807 on Earth. Okay, so we simply use this formula. Weight is mg. Okay, mass is 1 kilogram, and g is 9.807 at sea level, the standard value. So what is the result? 9.87 kilogram meter per second square. If you include this unity from the very beginning, 1 Newton divided by 1 kilogram meter second square, okay, you automatically get Newton, because these will cancel and you get only Newton here. But again, I emphasize, always write units in calculations. Okay. And another example involving some economics also. Let's say a school is using electricity, and this is the price of electricity, 12 cents per kilowatt hour. And they are using a wind turbine generating 30 kilowatts of electricity, and it runs 2200 hours per year. Okay. Now the question is, how much money will school save per year as a result of installing this wind turbine? Okay. Very nice, simple energy problem. Now we use, logic here. See, we didn't use any formulas for first law yet. Okay. Now what do we know? We know that the turbine generates 30. Okay, forget that. 30 kilowatts. Now 1 watt is okay, let's leave it at 30 kilowatts. Okay. Now this is power. It is equivalent to 30 kilojoules per second, right? 30 kilojoules per second. Why? Because watt is equal to joule per second. So how much energy is generated in 1 year? Or how much energy is generated if the turbine runs for 2200 hours? Okay. Energy is power multiplied by time interval, right? Or power is, again from high school, energy divided by time. Meaning energy is power times time, okay? And power is energy per unit time, which is 30 kilowatts here. And then time interval is 2200. If you multiply, what do you get? 66,000 kilowatt hour. Now, do we need to do a unit conversion here? Kilowatt times hour? No, because this also is known as a unit, kilowatt hour. Okay. So you ignore that dot in between right here. So the result is 66,000 kilowatt hour. Again, say the beauty of using units in calculations. 30 kilowatts, 2200 hours, multiply that many kilowatt hours. And this is a unit that we use in daily life. Okay, that means the school will save 66,000 kilowatt hours because that much electricity will come from the wind turbine. Now the school is paying 12 cents per kilowatt hour. Then what is the money saved? Again, logically, the total energy saved and the unit cost of energy, which is 66,000 kilowatt hours and 12 cents or $0.012 per kilowatt hour. Okay, do the cancellations, kilowatt hour, they cancel. What do we get? Dollars, how many dollars? $7,920. Okay. So the school will save like almost $8,000 as a result of installing this wind turbine every year. Now you see again the calculations, okay? That is, you use the basic knowledge, basic relations between energy and power and unit cost and total cost. And by simply using these simple relations, you end up with, solving significant problems. And engineers, often do such simple calculations because most people cannot do those. Okay, any questions on this example? No question. Okay. I'm not sure I understand. What is it? Any question here? Okay, everyone understands that. Okay, now let's discuss also state and equilibrium before we take another break. Okay. Equilibrium is a state of balance, and thermal equilibrium is really temperature equilibrium. If a system has the same temperature throughout, we say it is in thermal equilibrium. Okay. And mechanical equilibrium means no unbalanced forces. Phase equilibrium, no phase changes. Chemical equilibrium, no chemical reactions. That is no change, a state of balance. Okay. And a set of properties constitute the state of a system. For example, you have air, okay, here, 2 kilograms of air at 20 degrees, 1.5 cubic meters. Now, this is one state. If, let's say, this expands and the volume becomes 2.5 cubic meters, okay, and heat is transferred or something, and temperature, mass remain constant. Now, this is another state. Even if just one property changes, okay, one property changes, then the state changes. Okay. Look at this figure on the right. It is like 20 degrees here, 30 degrees there, whatever. Now, this is obviously, this system is not in thermal equilibrium because the temperature is not the same. And if you wait long enough, and if it is well insulated, the temperature will equalize here, okay? And at the end, it may become like 32 degrees everywhere, okay? Now we say, now here we have thermal equilibrium. But this on the left, it is not in thermal equilibrium. Now the question often rises is, to fix the state, how many properties do we need? And it turns out that for a simple compressible system, that is, if let's say the effects of gravity, I don't know, motion, surface tension, magnetism, whatever, if these effects, okay, are not relevant, you are not considering those, then the state of a system, it is called a simple compressible system, is completely specified by two independent intensive properties. Now, this is a very important state postulate, and we use this a lot in thermodynamics. That is, if you know two properties that are intensive, okay, and independent, they fix the state, okay? Now, intensive means doesn't change with the mass. It is like temperature, pressure, density, but not volume, okay? Specific volume is intensive. Temperature also is intensive. Therefore, these two properties will fix the state of nitrogen here. Okay, that is, any other property of nitrogen can be obtained using these properties. They must have fixed certain values. Okay. Now, process. If a system goes or changes from one state to another state. It undergoes, through some states here, as you see here. It is called a process. That is, process is a change of state. It can be small, it can be large, okay? And the states through which a system passes as it goes from state 1 to state 2 is called a process path. Okay? So to describe a process, we need to know the initial state, 1, the final state, 2, and the states that the system passes through, the process path. Then the process is completely described. As a special case, quasi-static or quasi-equilibrium process, if during a change, here the state changes, but if it is changing almost uniformly, like during a slow compression, the piston moves slowly so that the molecules here can adjust, okay? We call it a quasi-equilibrium or almost equilibrium process or quasi-static. But if you do a very fast compression, then you will have pressure, build up here. So the pressure will be higher than the pressure there. You may even have a shock wave here, some kind of explosion, okay? Then that process is not quasi-equilibrium or quasi-static, okay? So this distinction is also important in thermodynamics, the type of process there. And we have also special kinds of processes. Again, you remember from physics. If a property remains constant during a process, okay, we call it, we use the prefix iso. For example, isothermal process means the temperature remains constant during a process. Isobaric means the pressure remains constant during a process. And isometric or isochoric means the volume remains constant. And as a special case, if the state returns to the initial state after the process, we call it a cycle. Okay, it becomes a cycle dash. And as a special process again, if things change within a system by space, but there is no change with time, okay? No change with time at any point in the system, then we call that a steady flow process. For example, you may have a control volume here. This may be like water heater or some kind of whatever. Okay, and inside the temperature can be like 300 here, 225 there, 150 here, whatever. Okay, and let's say after 1 hour, again, no change spatially, same values. Okay, although they differ from one point to the other. Since there is no change with time, this is a steady flow process. Okay, so we will use also this phrase a lot in thermodynamics. If things are unsteady, then we cannot make that claim. So during a steady flow of conditions, the mass within the system remains constant, and the amount of energy within the system also remains constant. Although we have a lot of mass entering and mass leaving, but the whole thing is happening steadily. Okay, so we will take another break here before we finish this chapter. Again, these are concepts. Now, do you have any questions before the break?
Sir, can we take the slide?
Do you have a chance to give us this PowerPoint file? Sure.
We will, yes, we will give it to you later on.
Okay, thank you.
Yes, I think the assistant Mehmet Can, he will supply this after the course. Both this one and the one that we did in the first hour. Okay, any other questions? If you ask a question, make sure that you unmute yourself so that we can hear you. And after you ask the question, you can simply mute it so that we don't hear anything from your side. During the next hour, we will discuss temperature and pressure. So that will be the end of today's lecture. So no more questions? Okay, so let's take another 5-6 minute break. Okay, and then when we come back, we will finish this chapter. All right? Okay, I will see you in 5 or 6 minutes.